Hi guys, today I'm just gonna talk about what I learned today. So today the main topic is B3 and also it's about B3 but there's already big progress today. Um, uh, it's actually TMI and there's a kind of method that when I'm trying to learn something, rather than reading just kind of books because buy bunches of books, I print all of the research paper based on that keyword. Example, if I'm trying to learn about the B3, I search on the Google like the B3 research paper PDF, and I print all of the necessary PDF and I read it and I understand it. And I think that is kind of really better than the book because there's so many like missing link while reading books, so I prefer this. And today the I read like three research paper, but I didn't read all of things but because some of the information talk about in this research paper doesn't talk about like really unnecessary to me, so I'm just gonna do the cherry picking. Um, so there is the big progress, and I really wanna talk about this. Um, so if you're trying to learn about like indexing techniques, you're able to learn about like in-memory indexing and out of memory. And so out of memory is means that use secondary memory, which is like those kind of disk or GPU, not like also it uses GPU, and it also trans is also do the transition from the disk to flash. That's kind of out of the memory, but nowadays I think we commonly use in-memory indexing. Because the operating system also handles everything to us, so we just do the in-memory indexing. So indexing, what I just talk about indexing, index file is just a bunch of sets of record keys, and we somehow trying to make some kind of efficient algorithm data structure to find the target record key. So that's kind of that's called the indexing thing. And there's my common mistake about learning B3 was I just know the B3 they just trying to use they just search they traverse, and I thought they just trying to do when I trying to make the B3 insertion, I thought they just gonna put the query key into node and use a sorting algorithm and use short it, and if the correct target query key is gonna be for the used for the search, it just traverse for the and based on the comparison of the 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 size of the current the target query key and current key in the B3. I'm just gonna try to use this. I'm sorry, my English is really bad. As an example, so the reason why shorting is kind of important in the B3, you have 1, 2, 3. Example, you want to find let's say 4, 8, like 18. Example, you want to find number your query key. Let's say your query key is 3. So to find this kind of query key, you should check out the pointers of it. But how do we really check the pointers? You just really compare the 3 and the current key in the node. Example, 3 is smaller than 4, so you go to the pointers that are already defined, because in the 4 the smaller than 4 there's a pointer over here, and bigger than 4 there's a pointer here. So if it is 3, you go traversing this way, but if it is like 5, you go traversing this way. And those kind of thing is kind of valid because that means that we use the sorting algorithm for the every time we insert. Example, Because if it's not really shorted, for example, it is 8. If it is like 18 and 8. For example, I want to insert a 3. Example, I want to insert 18. And if it's like 19, let's say 19, but rather than traversing here, I traverse here. So there's gonna be like there's gonna be like, how to say it, inconsistent data. So we do sorting algorithm, but I thought they use sorting algorithm for this, and I found out that the modern B-tree, they don't use sorting algorithm for the insertion. If, example, you insert 3, you have to sort it, right? You have to sort it, and you have to sort it, right? And the modern B-tree, they use the key value rather than trying to do the sort. Sorry, my pronunciation is really bad. so if you look at object, so object is really kind of, let's say, hash map. If you're trying to find a 3, you can just use the key value pairs, and if the key is not being here, you can just find these smaller than these bigger than 3, and we can just go to the left part. But the problem is that, but it's very simple, and that is really efficient for the search, the single search. For example, you want to target 18. You can target 18. So rather than searching all of the necessary nodes, necessary key, we can just use the key value pairs and look up if the keys is in there. Example, you can just put it here, key value pair. But the problem is that, what if it is range search? If it's like we target 18, it's pretty fine. But what if you say, I want to get the value, the 18 to the 200? So what if it's like that? So that is why, rather than rely on some kind of like key value pairs, we just define as a BPA, which is it was like binary page. I forgot it. Hold on. Binary page array. Yeah, I think binary page array, but hold on. It was like here. Yeah, BPA. Buffer partition array. Sorry. So buffer partition array, they even make this metadata as a buffer. You never 4 byte, example, like those kind of thing. So to trying to use this, and we don't really have to think about like hash thing, because you already define this node as a page, and you also made this for those kind of thing as a buffer in syntax. For example, this is your 4 query key 4, and this like 8 here, and this is 18. So based on that, we don't have to use short sorting algorithm and the hash map, those kind of thing. You can just reuse these buffer made the page node layout, and you can just traverse it. Not traverse it, you can just find it based on the incrementing the buffer value, byte value. But what I really care about more is also B plus 3. I saw the B plus 3 is that rather than they use the key value pairs, they utilize the double linked list. Example, you want to find 18 to 200, and the normal B-tree, they're really bad at this. They could be bad. They could be good on the single search query, but if it is the range search, it's really bad. But the B plus 3, what they did was they made the doubly linked list, and make it traverse until it finds the leaf. And if this leaf is found, for example, if this leaf is starting point, you go back again rather than doing recursion stuff. You go back on using this double links pointer, and you find another leaf that inside of this 18 or 200 between it. So they utilize these double linked lists also for that. So that's kind of really efficient, and really, I think those who made those kind of data structuring algorithm is really efficient. They're really smart. And also for the range query, the B tree, their time complexity is gonna be O log B, O log B n plus, I think a plus there, it was like plus, and the k is gonna be your query keys. For example, 18 to 200 is gonna be your there's gonna be 182 keys, so you have to, that's gonna be k, and that's gonna be divided by 8 b. So b is gonna be your how many nodes you can hold. So how many you have, example you have like 200, example you have 200 range of k, but if your node can hold three keys, so that's gonna be 200 divided by 3. So that's why this kind of time complexity is gonna be handled. And I also believe that this is kind of this also means that search, I think it was like search, not search. Yeah, I think it was like KB, yeah. Not search, but it's just like, so the B plus tree and the BPA is they're trying to even reducing this kind of time complexity. So this is it. Have a nice day. See you next time. Bye bye.